Thank you. Thank you. Everybody get 100%? I hope so. So that looks right. Let's just go through it just real quickly. I do expect that we kind of know our prerequisite material. It makes doing probability theory in this class a lot faster. So, but let's just run through this. So this is just f of x dx. So if you like minus infinity to infinity, throw it down. So obviously I could have made the bounds kind of a problem. It's not what I'm focusing on. So we'll just make sure that they're just the same things, that you don't have to transform the bounds or do anything to it. So what's this thing right here? We don't know if these are equal. So I'm just going to write it all out. So this interior expectation is the integral of x with respect to its joint distribution. So that's this thing, dx. And then this outer expectation, right here, this one, some integral sign. What am I integrating with respect to? It's this thing with respect to this thing's distribution, and this is a function of happy face, right here. So this is f happy face, e happy face. So that's what it is. If you'd like me to throw down all the bounds, you could do that. So now I can just rewrite this. I can slide that in, no tricks up my sleeve. So it doesn't have anything to do with happy face, that integral, so we can slide them into each other. Integral x f x given happy face. F happy face. So dx d happy face. So bounds. This is the joint distribution. This is fx and happy face. So I can substitute that in. And now what I want to do is I want to exchange the order of integration. Why can I do this? Can you always do this in every case out there with every integral? You can't. So there's theorems out there that tell us when we can do that. Anybody in the stats department or a math major or something like that know why we can do it here? Yeah, so it's if I would have had this finite, it's guaranteed. So you can always do it in that case on compact sets. But it's a little bit questionable sometimes when they're infinite. You can always do it when the function is positive on the inside. That's not the case here because we have the x sitting in there. But you probably want to look at dominated convergence theorems. So there are early parts of Casella and Berger, but we usually don't teach through that stuff, and we usually teach this stuff later in measure theory. And so I'm going to skip over it just like everybody else has, and just say this is Fubini's theorem. And what you could do in any particular problem is just check that the answers are the same when you check the orders. But there are theories out there. For this, you can do it. So for expectations. So I'm not going to go into all the measure theory, but if you're interested in that sort of thing, you get caught up in the weeds of every problem, you might want to be more technical and more theoretical and ask yourself these questions. So, but if I can do the orders, redo the order, I'll just happy face first. I think this is why people don't use happy face as a variable. So it's hard to do. dx. So x, joint distribution, f of x, and happy. I can pull this x outside, no tricks there. It doesn't have anything to do with the inner integral. So same thing we did over here. We slid that across. So the x can come out, don't need any theory for that, just has nothing to do with what I'm integrating. So we pull that thing out, and this thing right here is the marginal distribution fx. So we're right back there. So a lot of these proofs and identities work this way. Write out the left side, write out the right side, see that they're the same. No assumptions needed. So other than a little bit of theory and knowing what we're doing. So hopefully everybody got that. I'll just double check, but this really just is a placeholder if this is difficult, or if you know how to do it and you don't think it's difficult, but you need a reminder, it's telling you where to go refresh in your probability book. So we've applied this to posterior predictive distributions, and I promise you in the future, using that trick will save you a lot of time. So doing the integrals takes sometimes a lot of time on a test. So that's just a heads up. Thank you very much for indulging me. Welcome back to the class component. So the lecture component. I think what I was saying at the end of last time was a little bit fast. So let me slow down and just regurgitate what I said before. So confidence interval. These are coverage intervals. So they cover at some frequentist rate. So anybody that ever says they're a frequentist, ask them what the frequency is. Ask them what they're counting, what is the, and if they just say, oh, my basic notion of probability is frequentist, that's, everybody kind of feels that way. So if you had the opportunity to observe frequencies, you'd probably want to calibrate whatever you're doing to that. So sometimes there's asymptotic intervals, asymptotic things, and I never really like that argument too much. I would want to know that the asymptotics are so good that it converges super fast, but I never feel like taking that theory for granted, and I always do a simulation study to check how well things work and what are the limits to your analysis. So here's an example. Well, I'll just say, for our example, we'll just take xi's are normally distributed with mean mu, variance sigma squared. Everything's IID, we get to see I goes from 1 to n. And so a good estimator for mu is x bar. There's all kinds of good reasons for liking this. We don't even need the central limit theorem in this problem. So x bar is normally distributed. It's not asymptotically normally distributed, but very often we'll do the same sort of stuff for models where the distribution isn't normal, and then we're asking about the asymptotic interval. Good example of that is the binomial. So, which is kind of interesting for all kinds of weird reasons. So the binomial is like P lives between 0 and 1, and using a normal approximation, even a Stat 101 student in elementary school could say, wait a minute, is that really a good idea? So asymptotically, sure. But for what size n would you actually do that? And my answer is, I'd never do it. Anyway, so idea is that we're going to build some interval. We're going to do the typical thing, 1.96 is special to a normal distribution times its standard error. So we're going to get left and right bounds. So for a sample size of n, I can collect some x bar right here. So, and then I can construct an interval. So let's say this left-hand bound is this point right here, and this right-hand point is this right here. Question is mu right inside of the bound, between these bounds? So, and this should happen some amount of the time. It should happen 95% of the time, and that's where this number comes from. So just to be clear, normal distribution, standard normal, centered at 0. If I go out 1.96 standard errors, and I go in the other direction, minus 1.96, this will have 0.025% of the mass in that tail, and this will also have 2.5% of the mass This right here is 95%. So this is being unstandardized. You might think of that. So now I have a normal distribution that's centered somewhere, not 0, and I've got some standard error attached to it. So just a location shift and a scaling to the problem. And so we can repeat this exercise. I can go out and collect another n data points, come up with another x bar. So let's call this one based off of x bar 1. I can do it again, collect x bar 2, construct its bounds. It's off of an entirely new data set of n data points. I probably should make these intervals exactly the same width as each other, because all I'm changing is the location in it. Since everything is normally distributed, we're not estimating the standard error or anything like that. This is just shifting of this interval. So let me make this a little bit better looking. So maybe this is x bar 2. This comes over a little bit, so these intervals are kind of bouncing around a little bit. I could do this a lot of times. You can imagine maybe I do this zillions of times, and I come up with these intervals right here. You can imagine them going all the way up. And some number of these will cover mu. The way I've drawn it is all of them have covered mu. And we might expect that if there were just like 7 of them or something like that. So periodically, we'll get an interval out there that doesn't cover mu. So this one is shifted over. So this does not cover it. So a confidence interval, the idea behind it is it's a process monitoring sort of construction. I'm monitoring the whole process itself. I'm trying to think about this in some lens where I get to repeat the process over and over again and see if the process is doing the same thing. And I would agree, if you're doing quality control, you'd be inclined to think this way. So let's just monitor this stuff, and if these intervals are bouncing around in extraordinarily different ways, something's changing in the process.
What if the intervals are the same, but the way the data moves around within that interval changes? So like an example that I'm thinking of is like, say we have a mean, and in one case our variance is set, and like it's within that interval, and the variance is because of a uniform distribution of the data. But now take another case where the variance is still the same, like the maximum of it, but now it's all scribbly and all of that. So how would this account for that?
You said something in the middle of there. You said our data is uniformly distributed.
In one case.
In one case. See, my case is all my data is normally distributed, coming out of the same process.
Okay.
So if I had all of a sudden data coming in from a uniform distribution, that's a different process.
Okay.
So that would not be an IID setting. Now I hear what you're saying. You might have two different processes. And you might want to say, I want to figure out which process it came from. Save that for mixture models. So think about that mixture model thing, that I can have mixtures of distributions and figure out which process they're coming from. So we will study that problem in some sense.
Okay.
So this is a slightly different question.
Okay.
So this has this assumption built into it, but if you weren't sure, you'd have to adapt the model itself. So I'm going to say, and this is the one fiction I get to repeat over and over in this class, is that's true. So in the real world, we don't know. So we look at data and we start to surmise what distributions could this be coming from, and is that process changing? We were just having this conversation the other day. It might be it's two different processes and we don't know. So how do you figure that out? A lot of experimental checking to build your model in the first place. So that takes a lot more time than just writing this on the board. I'll give you a tool later to answer that question.
Okay, thank you.
So anyway, this is the idea. So what we're really doing is, at the end of the day, we usually just give back one interval. We're thinking about this conceptual process. And the question is did it cover or did it not? And you don't know because you don't know what mu is in the first place. You could concoct a simulation study and show that 95% of the time these intervals cover. And if you crank up the number of times you repeat this will converge to 95%, no arguments. So really the confidence interval sort of construction is a statement about the process, me going out and giving intervals to cover the truth some percent of the time. Who's the 5% that gets the bad intervals? And if you're an asymptotic interval constructor and you're a frequentist, how many really got the right intervals? We don't really know. So unless you go out and check. So that's one viewpoint. I've always struggled with this. So, because I'm like, what does it mean about the actual analysis at hand? So, and a lot of people like to interpret this as say, what's the probability that mu is inside of the interval? And the question is can you actually interpret it that way? And I think you can, but you have to turn yourself into a Bayesian for a second and make a probability statement about mu itself. So I'll just point out that the probability statement that this interval is constructed on is just this thing right here, where we're going to look at x bar and check to see if it's between some bounds. I'll just hypothesize about what mu is right here, and I can make this statement. This is mu naught 1.96 times the standard error. This is mu naught plus 1.96 times the standard error. We could compute, this is actually 0.95, and this is 0.95 because this is random. And it's normally distributed, and we know properties about the normal distribution. We can rephrase this and write this down like this. Sometimes people will do this. Write it out this way, x bar minus 1.96 times the standard error. X bar plus 1.96 sigma over root n. If this statement is true, this statement is also true. So they're equivalent probability statements. What is this probability statement about? Again, the only random thing in the equation, at least through our conceptualization as frequentists, is x bar itself. So it's this left bound and this right bound that are random, which is what we're drawing over here. So it's a statement about going out and collecting more data and what would have happened if we collected more data. So this is called pivoting. I don't talk too much about it, but I think the name is at least conceptually, there is a technical definition to this, that you have to pivot around a parameter that doesn't have anything to do with the parameter itself. So a statistic that doesn't have anything to do with the parameter. I'm not going to go into those details, but you can see I've rearranged everything and I'm calling it a pivot. So there are correct ways to do it and bad ways to do it. This is still a correct statement. I think that I sympathize with our old Stat 101 students thinking this is a probability statement about some mu, especially when they take off that. And it's like you shove that thing in the middle and you're talking about the importance of that. But again, it's just the bounds that are bouncing around, and that's the random bit. If you're a Bayesian and you were to do this problem, you go through all of that argument to upgrade mu to a random variable. And the only way you can do that is through Bayes' theorem. So I construct pi mu, given all of my data. I could just use x bar if I wanted to, because after I know sigma squared, x bar has all the information about mu. If you didn't know that, you could just formulate the likelihood function and work through the product form. You'd get the same answer. But this thing, what we derived last time was this one, or several weeks ago. This is x bar sigma squared divided by n. And this had an assumption that we used the location invariant prior, i.e. the flat prior. So this is what we came up with. This is the posterior distribution. Draw this normal distribution. X bar is in the middle. I go out some distance. This is sigma over root n using my old convention. So same standard error on everything. And I would construct my interval and probably pick the highest density area in everything and build this up so it's 95%. I would agree you could budge around this interval. I could slide this over to the left a little bit and drag that way into the tail and add up 95%. That'd be another way to do that. It wouldn't be as good of an interval because it's not in the densest part of the space. So another way to say that is it's not the shortest interval you could come up with. I'll talk about those definitions later on, but I think it's appealing to have the shortest interval describe where mu is versus a really long one. You can imagine I can budge this way down here and move this over just a little bit. You know, that wouldn't be as good of a 95% interval, but it's still a Bayesian interval. So we might want to impose that we have the shortest interval. So how far would I go out right here? 1.96 times the standard error. So this is x bar plus that thing. And there's an associated left-hand bound, which is x bar minus 1.96 times the standard error. What would you end up getting right here? This would look exceedingly similar to what we wrote down. So we would write down the probability on mu, x bar minus 1.96, up to x bar plus 1.96 times the standard error. Times the standard error there. And this right here is 0.95 as well. And you'll probably stare at this thing and go, aren't those the same statements? But there's a conceptual leap that's being made that the Bayesian is making a probability statement about mu, and the frequentist is making a probability statement about the left and right bounds. At the end of the day, you come up with the exact same bounds. The Bayesian is saying the probability statement is about mu, so this is a belief statement. So the intervals are belief intervals, and they're statements about where you believe mu lives. So under the flat prior, we get the same interval, and what I would like to do is instead of begging my old classical teacher, could I please just say, is the probability statement of mu is in the interval? I'm going to say it is, because I'm a Bayesian. I used a flat prior, and I will even give you what you want. It's also optimal frequentist in terms of coverage. So that's the both worlds. So the Bayesian can be a frequentist too, and come up with the same analysis as somebody else. This was probably the most annoying thing Bayesians have ever done, is go to everybody and say, oh, all your analyses that make sense, they're really Bayesian analyses. So I don't think anybody appreciated that, but there is an alignment right here. And so both camps get to be happy with themselves. And you could appeal to me as a Bayesian and say, if you wanted to interpret this as mu is inside the interval under the flat prior, you could do that. That's not always true. Keep in mind, for a normal distribution, mu and x bar are totally symmetric in each other. And the prior that we're using is perfectly symmetric as well, it's flat. So there's a certain symmetry to the normal problem that makes us all agree with each other. So oftentimes that's not the case. Let me show you one such case. So this is an example. Bayesians and non-Bayesians totally agree with each other, slightly different interpretations, but I don't see there anything to fight over. You can have the best of both worlds. What's wrong with that? But academics, they'll fight anyway. Everybody agrees? So we just think about it differently? Let's get into a huge fight. Here's something people might fight over. This is probably a Bayesian setup, you know? So there's a paper on the website called Could Neyman, who is it? It was Neyman, Jeffries, and Fisher have agreed. Are those the three names? I don't know which order they come in. Could Jeffries, Neyman, and Fisher have agreed? You guys seen that paper hanging out on the webpage? There's a PDF waiting for you. So this is all from that paper, and there's a lot of things being said in that paper, and they talk about something called the conditional frequentist that solves the problem where you condition on an ancillary statistic, but nobody has a general paradigm for doing that. So, and that's the argument they make, and they say, if you condition on your data, you're conditioning on all the ancillary statistics and the sufficient statistics, and Bayesians do that for free. They do it through the likelihood function. So, anyway, let me show you probably the most compelling example that's in that paper. This is an example where Bayesians and frequentists disagree. In fact, somebody wrote a paper one time and asked me to be a co-author on it, and they were kind of taking the frequentist side on it and seeing if they could appeal to me, and I kept kind of saying, get this thing out of here. So my name's not on it. I didn't agree with what was being said in there, so people can still argue about things. So still friends with everybody. So they have a different opinion. They used this example and had a slightly different take on it. I still thought it was nonsense without doing the correct Bayesian analysis. And so we'll show what the correct Bayesian analysis is here. So let me give you the problem setup. Xi is going to be one of two things. It's either going to be theta plus 1 or theta minus 1. This will happen with probability 1/2. We could change these numbers later and talk about what the significance of the numbers are. But I'm kind of changing a typical binomial problem to let you know what the probabilities are, but I'm not letting you know the location of everything. So that's a little bit different than everything. So this is shifting around. I'm going to see one of two parameters, and I don't know what this location parameter is. So this is a location parameter. Theta will live between minus infinity and infinity. So we don't know what it is. And our goal is to guess it, to figure out what it is. So I'm only going to let you see 2 data points. We could let you see more. If we let you see too many, they might agree with each other. So we'll keep it to the point where sometimes they agree and sometimes they don't agree. Okay, so let me just tell you a fact. This is a 75% confidence set. So a set is just points inside of an interval. Okay, so I'm going to give you some points back. I can use the same concept. It doesn't have to be a connected interval. If I had a multimodal distribution, I'd be inclined to give you disconnected intervals back. So a set of intervals. This is going to be a set of points. So even simpler than that. So just as an aside, we don't always give back one interval. If I had something like this, let's make this really deep. So there's almost no chance to bridge it. If I gave somebody an interval that looked like this, I'd be pretty disappointed, So I probably think you should give me an interval that probably looks like this. We will see that later on when we talk about highest posterior density intervals, i.e. shortest interval sets. So here's a 75% confidence set. I'm just writing it down. It's going to be a function of x1 and x2, so I'll just write it out the typical way. So C for confidence. And this looks like this. So it's going to be x1 minus 1 if x1 is equal to x2. So I could have written it down as x2 minus 1 as well. Or if x1 is not equal to x2, I'll give you back this. So let's just rethink about this in terms of a process and what the question is that's even being asked and what this answers. So this is saying that if I use this construction right here, and I believe this, it's saying that I will nail theta 75% of the time. So if I repeat this experiment, go out, collect 2 data points, compute my confidence set depending on if x1 is equal to x2 or if they're different. I give you one of these numbers. This process should hit theta 75% of the time, meaning if I go out and I repeat it, I collect another 2 data points, I compute a confidence set, I collect another 2 data points, I compute a confidence set, I do that over and over again, I'll get the right answer 75% of the time. Let's verify that to ourselves. How often does this happen? 2 out of 4 times. Anybody want to rephrase that? Half. Yeah. We can come up with all kinds of ways to say it, but it's a half. This happens with probability. 1/2. Let me give you another argument. I'm not sure what you're thinking about with 4, but it's correct what you said. So how often do I get this number? Who cares? I'm going to get one of these 2 numbers. So I'm either going to get this one or that one. So on the next draw, what's the probability that I match it? So I can just think about one draw from the process to argue this. So I'm going to get something on the first draw. X1 is some number. What's the probability I match it? It's 50-50. So no other possibilities. So this also happens with probability 1/2. That's how often I will report this back and how often I'll report this back. How often is this right?
All the time.
Yeah. 4 out of 4. So this is 100% right here. Let's just check. This is going to be maybe it's theta -1. If that's theta -1, then this is theta +1. I add those 2 things together. That's going to be equal to 2 theta. Divide by 2 theta. So that's theta. Always happens that way. How often is this one correct? Yeah, so 50% of the time. So I'm just asking how often is that right, conditional on us picking this. I heard what you said, you're right. You producted those 2 things right into each other. So if this was true, how often is this right? I'll just rephrase. 50% of the time. So this would be right if x1 was the theta +1. I could have arbitrarily changed the rule and made this x1 +1, and that would have been right 50% of the time. But all I'm saying is this is a 75% confidence set. So this is true 50% of the time. So 50% times 1/2 is 25, plus 100% times 1/2 is 50 plus 25. That's 75. So this will land on theta 75% of the time. So this is what a confidence set or a confidence interval, this is what the idea of the probability statement is about. It's a statement about the process. It is not a statement about what you actually believe theta to be. So is this a good answer? I think no. I think it's a horrible answer. And the reason why is because it's not conditional. So on which event happened. So sure, I could report back these answers, but if you're using the pure blind sort of frequentist thing, and I don't want to debase all of my frequentist friends, because I don't think any of them would give this answer. They'd give a slightly different answer, probably. So, but just my point is in the literature of confidence intervals, it doesn't exactly guard against anything like this. So that paradigm doesn't say this isn't an appropriate answer. This process covers 75% of the time. So what are you supposed to report back? The confidence level, 75%. So I go, I flip the 2 coins, I get back some x's, and then I notice that this is true. x1 is not x2. I compute this number, I hand it back to somebody, and I say I'm 75% confident. So that confidence word is weird. What does it mean? Nobody knows, you know? So it's this pivoting sort of thing. What is the probability statement about? It's not about theta, it's about the process of collecting data and repeating it. So I will give back correct answers to 75% of the people if they keep coming in and playing this game, and I give them back these numbers. And 25% I'm leading astray. So I would rather, every time I saw this, tell people I'm sure. And I would rather, every time I saw this, to say I'm only 50% sure about that. And there's another answer I'm 50% sure about. I think that would be a better answer. So altogether. So because it's conditional on what's actually happening and it's a statement about theta. So I would argue this is a bad answer because you'd always report back 75. If x1 and x2 came in, they're the same, I give them back that, x1 minus 1, and I say 75% confident. For me, I feel like that's supposed to mean, I feel inclined to say I'm 50% sure. And there's another answer I'm probably 50% sure about too. I think that would be a better answer, but I'm really making my probability statement conditional on these two events. And I could derive an ancillary statistic that tells me which one happens. It's actually x1 minus x2. So is the distance 0 or 2? The absolute value of that. So you can build a frequentist analysis conditioning on the difference. If you know what an ancillary statistic is, great. If you don't, it means the probability distribution about that statistic doesn't involve the parameter. You can check that the difference here doesn't involve the parameter. They just get knocked out when you difference these things. So you can build a conditional frequentist analysis that I do think makes more sense. And the paper does go into those details. And if you want to skip it, that's totally fine. So let me give you another way to think about this problem. Let's watch what a Bayesian does. Josiah, you want to say something? No? Anybody want to say something? Sense that wrong. Okay, let's look at what a Bayesian would do. There's really only two things that a Bayesian does, right? All Bayesian analyses are a superposition between two ideas. So the first one we have very little choice over when we're in the classroom. Obviously, we need to build a model when we have real data and it didn't come from a textbook, just like what you're talking about. So step one to a Bayesian analysis is what? Yeah, prior likelihood. You pick which one. I like to upgrade the importance of likelihood. I'm not willing to establish priors until I've seen the meaning of the parameters, I understand what they're about, then I can make some choices about them. So somebody just says, there's a parameter theta, what prior would you pick? I have no idea. It's positive. Okay, well, I guess that helps a little bit, but I still have no idea. So I'd have to know what the model is. But I'm going to say we're going to write down the likelihood function. This is just x1 and x2. And then we need to pick a prior. Just real quickly, which prior would you pick? You've kind of seen the likelihood function. It's all right here. If you think about it right, you probably want to write it down a little bit more sensibly. But which prior would you pick? I'm already prepared to make a choice. Jared is too.
Since we already decided that it was a location parameter, I would just choose that one prior.
Yeah, maybe flat. So I don't know what it is. It's on this whole continuum. So maybe flat, we could come back and address this later on, but maybe proportional to 1. I'm just going to write down the likelihood function real quickly. Let you guys chew on it over the long break, and we'll come back and we'll finish this analysis here. But let me just write it down for you. This is going to be proportional to I goes from 1 to 2 fxi given theta. Now I need to write down this probability statement. I'll make it a PR, probability, so that it's this thing right here. Xi is equal to theta plus 1 and theta minus 1. Each has probability 1/2. So what's this? What's that? 1/4. So the whole thing 1/4, 1/2 times 1/2. So multiplying together, this is 1/4. Is that right? I'll give you a huge heads up. There's no theta in the equation. This is what everybody does year after year. You're definitely not alone. So it's not a quarter. There's no thetas. So you're saying that the likelihood has no information about the parameters. Let me just revise this for you and say that this thing right here is going to be 1/2 to the, right here, this would be, I should probably write delta theta plus 1, 1/2 delta theta minus 1, but I also need, this is what you said before, they're just always 1/2 no matter what. I also need the indicator function that where theta lives and how the xi's are connected to them, and that comes from this right here. So delta function xi is an element of theta plus 1, theta minus 1. So it has to be one of those things. And I can rephrase this. This can be the delta function, the indicator function. Theta is an element of xi plus 1, xi minus 1. Just rewriting all of that indicator function. This part actually has nothing to do with the problem at hand. So the 1/4 part of everything. So again, everything's up to proportionality, so we don't need that. These indicator functions represent the likelihood function. So the product of these two indicator functions. You can try to mentally draw that for yourself. But if x1 and x2 are different numbers, that delta function is a point mass. So we will illustrate this next time. If those numbers are the same, there's 2 point masses. So just work through the product of these two delta functions. So you're going to be producting those together. So this is the likelihood. So product of these things, I goes from 1 to 2 on these right here, and I don't need the 1/2 and 1/2. We'll come back to that next time and make sure that we all understand it and draw it out properly. We're down to our last minute, so I'd like to give you some feedback back. Here are your homeworks. I'm just going to hand these back and get to know your names just a little bit better.